Hey folks, Mrs. White here. This will be our second remote learning lesson for stats and the final one for this week. So if you did not hop on during office hours Wednesday, yesterday, and you have any confusion about section 11.1 or section 11.2, please try to attend office hours tomorrow from 4 to 5. If for some reason this time doesn't work for you and you are confused, please reach out, okay? That's going to be a big part of you guys being really successful during this. You have to let me know if something's up because I can't read your body language. I can't hear you complaining about it in the halls. I'm not going to know if you folks don't tell me, so please reach out. Today we are going to start off with a sit and begin, and it's going to cover sample size, the type of sample size calculation that you would do from section 11.1, and we'll talk about how you can acknowledge and recognize that. Then we're going to hop into the next section in our book, which we're going to be looking at two samples again. So it's familiar and similar to what we did in the first section, but now we're going to be looking at means or averages, and they're going to be from samples that are dependent. And we talked briefly in the previous lesson about how can you determine if something is dependent or independent, and that's really going to come into play in section 11.2, and then in 11.3 where we look at independent means. So you have to start kind of making that delineation when you start tackling the problem. Today should be reasonably quick. We're going to cover two things. We're going to look at hypothesis testing and confidence interval for these two dependent means. Attached to this video you should see two things. One of them is going to be the examples that I'm using in this presentation, and the other is some screenshots of the homework problems in case you want to have that kind of as a sheet so that you can keep it in your notes, and or if you don't have your hands on your book right now, you can still complete the homework assignments. So let's get started by taking a look at our sit and begin. So in this problem, if we read it, it says an educator wants to determine the difference between the proportion of males and females who have completed 4 or more years of college. So right now, I see that it says difference, and it says males and females. So I know that it is two samples. In addition to it being two samples, I see this word, proportion. So I'm thinking I'm going to be comparing two proportions, males and females, from two separate samples. I'm going to be tackling it like I did in 11.1. So in order to be able to do this, I'm just going to continue on. What sample size should be obtained if she wishes to estimate, if she wishes the estimate to be within 2 percentage points with a 90% confidence, assuming that, and then we have two parts, A and B. Now in A, they're saying that she has some sort of prior estimate, okay? So if you have a prior estimate, you use a different formula than if you don't have a prior estimate. So let's start off by looking at A. Okay, and this is something that is not in your fold out. This is something you just got to kind of commit to memory. The formula for figuring out sample size, if you are given prior information, starts off with you looking at the proportion from your first, okay, and taking the proportion of that not happening, and then you add it to the proportion from your second sample times the probability of that proportion not happening, or the percentage, right, excuse me. Then you're going to take that whole shebang, okay, this whole piece, and you're going to multiply that by the z-score of your alpha divided by 2, all over your margin of error. And then here, again, it's squared on the outside, not the inside of those parentheses, on the outside. So a handful of these things we can plug in right now. Our proportion from our first sample, they tell us, and again, it doesn't matter if we make males or females first or second because we're adding. So we can say that it's going to be 0.275 times 1 minus 0.275, which is going to be let's see, 725, right? So 5, that'd bring it up to 8, 2. Yep, I think that's good. So we're going to multiply those two things together, and then we're going to add to it the proportion of our second thing happening, 0.231, times 1 minus that. So that's going to put us at 0.769. Okay, and then we're going to sum both of those things up. So we'll start off by multiplying. I do not have this pre-solved, so I'm going to do it on my calculator. 0.275 times 0.725 gives me 0.199375, so I'm just going to round it to a 4. And then I'm going to take 0.231. I'm going to times it by 0.769. And I get 0.17763, or just 6. And if I add those two together, so 0.1776 plus 0.1994, I end up with 0.377. And I'm going to times that now by whatever I get going on over here. So to find my z-score of my alpha divided by 2, I'm going to look in the back of my book. I'm going to go to table 5. And in the bottom, let's see, left corner, it says confidence interval critical values. And I actually use these same critical values to find my alpha divided by 2 here. So if I look there, I'm dealing with a 90% confidence. So my alpha is really 10, or 0.10 divided by 2. Now using this table, I don't even need to know that it's 0.10 divided by 2 because it says 90% confidence. So if it's 90% confidence, I'm dealing with a z-score of 1.645 all over my margin of error. And they want it to be 2 percentage points, so it's going to be 0.02 and then squared. So I'll start by doing that division. I'm going to do 1.645 divided by 0.02, and that gives me 82.25. I'm going to square it. And that's giving me 6,765.0625. I'm going to multiply that right now by 0.377. And I get 2,550.428, blah, 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 blah. Okay? Now, the important piece to note here is that you can never have a decimal part of a person. And so I'm always going to take this, and regardless of what it is, I round up because it's the minimum. So I would need a minimum of 2,551 people. Okay? So this is actually more work than what you would need to do for part B. Okay? In part B, and let me just actually switch over to orange. In part B, because you don't have any prior estimates, you're going to automatically use 0.5 instead of doing all of this work to get this number. And you're going to times it by the exact same piece that we have here. Okay, so our confidence interval hasn't changed, right? It's a 90% confidence, so that z-score is the same. It's still within 2 percentage points, so our e is going to be the same. We're still going to have to square it after the fact. So we're going to end up with 6,765.0625 in there. And if I take those two things and I multiply them together, oopsie. So I got that 6,000. I'm going to times that by 0.5. I end up with 3,382.5 people, which again, every time we have a decimal, we have to add up, or round up, 3,383 people. And if you remember from a previous chapter when we did sampling strategies, we always rounded up there. But we also found that when you have a prior study, okay, like in part A right here, if you have a prior study, you're usually going to have a smaller sample size because you have something to work off of. If you don't, and you're just automatically using 0.5 as that coefficient piece, then you're automatically going to have more people, okay? Okay, folks, so let's start off talking about 11.2 now. So again, we're going to be looking at 2 different samples. And the data that we're gathering and conducting this hypothesis test with is going to be means. Moving forward, every time we have more than one sample and we are dealing with a mean, you have to ask yourself, is it going to be dependent or independent? And that's going to be one of these 4 items that we start looking for every time. Today, it's obviously going to be dependent. When we get together next class, it will be independence. So let's take a look at this word problem. Professor Andy Neal measured the time in seconds required to catch a falling meter stick for 12 randomly selected students, dominant hand and non-dominant hand. Professor Neal wants to know if the reaction time in your dominant hand is less than the reaction time in the non-dominant hand. A coin flip is used to determine whether reaction time is measured using the dominant or non-dominant first. Conduct a test at a 0.05 level of significance, and they give us raw data. So first things first, we're dealing with 2 samples, dominant hand and non-dominant hand. Were they gathered randomly? Well, yes, they were. So it is random. It says so right here. Next thing, and this is kind of what's different than in the past, is if we realize that we're dealing with two means, we have to then define, are we dealing with an independent samples or dependent samples? So hopefully you can take a second to think about this. Your dominant hand, okay, you know that, right? If you're either right-handed or you're left-handed. Your non-dominant hand, the answer to that question depends on your dominant hand, okay? So your dominant hand is defined initially, and then your non-dominant depends on whatever that one is. It's the opposite. So again, dependent samples. That's going to be one of the new things that we're adding with this idea of two means. Next, we need to make sure that our sample size is big enough. So is our n greater than or equal to 30? If it is, you keep going. If it is not, you need to check a couple things. You need to look for outliers by making a box and whisker plot on your calculator. You need to check if it's somewhat normal, okay, by looking at your normal plot. And we'll review those because as you can see here, there's not 30 pieces of data in our sample. Okay. Next, we would need our sample size to be large, but we don't want it to be too large. So is our sample less than or equal to 5% of the population? So here are the four things we're going to be looking at. Really, this is the only new one. We always did these other things for means. The next piece of information that we need to look at, or that we usually do at this point, is defining our null and our alternative hypothesis. And this is a little bit trickier as we're dealing with two means because it's going to be a little counterintuitive, okay, at first. So our null is always still going to have an equal sign. And if we want to say that our dominant and our non-dominant hand, they react the same, right? The difference between them would be nothing, okay? Now, I used an important word there. I said the difference between them. Like if we were to subtract both of them, our difference would be 0 because there's no change. And the way we model that is by using our mu, and then we put a little d here. So this means the average difference, okay? The average difference would equal 0. Now, part of you, just like part of me when I started this chapter, wanted to do this. The mean of my first sample equals the mean of my second sample. Because this is what we did when we were dealing with our proportions, right? This is not how we handle dependent samples. We cannot do this, okay? It is not an option here. As we're doing all of these problems, you're going to see that we're going to be using the d a lot, okay? Because what we're going to be doing is calculating our differences. So this isn't too bad. Generally speaking, our mean is going to equal, our mean of our difference is going to equal 0 almost every time. Now our alternative can be two things, right? It could be left-tailed, right-tailed, or two-tailed. So greater than, less than, or not equal to. In this problem, if we take a look up here, it says that he wants to see if an individual's dominant hand is less than the reaction time of the non-dominant hand, okay? So if we're doing a difference, we're subtracting. If our dominant hand takes less time, okay, than our non-dominant hand, which would have to take more time, what type of number would we have here? Okay, so less time would be a smaller number, more time would be a larger number. A small number minus a large number means we're going to have a negative, right? So that means that our mean of our difference, okay, in relation to 0, if we want it to be a negative number, right, we're saying it has to be negative. We find those differences, and the dominant is going to be smaller and the non-dominant is going to have more time because it takes longer, okay? The difference is going to be negative. It's going to be less than 1. In the past, hypothesis testing has been one of the easier things, right? You know your null is always going to be equal. You know your alternative is going to be one of the other symbols. I think when it comes to means, at least for me, this is a little bit trickier. So slow down and make sure that you're thinking about what type of number is it going to be. Is it positive or negative? And then that dictates really what your symbol is going to be here, okay? So we have our null, we have our alternative, we know that our alpha value is going to be 5%. So at this point, because we have a small sample size, because we're given raw data, I hope you're anticipating having to plug in this data into your calculator. And if you're not anticipating that, I'm sorry, that's what we're going to do. So grab out your graphing calculator. I have one here. It's going to take me a couple minutes. I'll probably speed it up. We're going to put our XI, which is our dominant hand information, into our L1 and our non-dominant into our L2. So I'm going to go stat. I'm going to go 1 for edit. And then I see my L1 here. Okay, so I'm going to take a second. I'm going to plug all of those in. Feel free to do the same for yourself. If you need to, pause the video. Now I'm going to go through and put all my values of non-dominant in L2. All right, folks, now that I've input everything into L1 that I need to, and everything into L2 that I need to now calculate the difference and put that into L3. And although that does not seem fantastic, it's actually not horrible, because we can treat it like an equation. So if I have L1 here, L2 here, I'm going to go up to L3 and see how at this point right over here, oops, okay, I can actually type something in there. There's an equal sign. So I'm going to put in L1 by going second L1, and I'm going to minus from it second L2. So you actually don't have to do all of those differences by hand. Now really quickly, as we look at this, if we see a negative number, if we're doing this minus this, right, that means that our dominant hand, our L1, was smaller, because when we subtracted that from it, we got a negative. That means our L1, our dominant hand, was faster. So we can see in our first option it was faster, smaller, faster, smaller, or excuse me, faster, slower, faster, slower, faster, slower, faster, slower, faster, faster, faster. So we want to see if it actually is statistically significantly faster. Okay? So let's go back to let's see, our presentation. Okay, so now that we've input this into L1, we input this into L2, and L3 we have our difference. Okay, now since all our data is in, we're ready to start doing our hypothesis testing. Now we can do it with both the classical and the p-value. Okay. But just like yesterday, what I want to encourage is that you use your calculator to figure out your test statistic. It's going to save you some time. It's pretty gnarly calculation, and your calculator does it for you, so we're not going to stress about knowing it by hand. Okay? So to run this hypothesis test, you're going to go into stat. You're going to go into test, just like we have for all of our other hypothesis tests. And what's cool about this mean is that we are actually going to go right to our second option, which is t-test. It's the exact same thing that we did before when we were dealing with means. Okay, it's literally the exact same keystroke. The only difference is that when they talk about your list, you need to make sure that you type in your L3. So let's take a look at that right now. Okay, so I'm going to go into stat. I'm going to go over to tests. I'm going to go down to number 2, which is t-tests. I have the raw data. I'm going to select the raw data. My null is 0. However, my list is no longer L1. I want to be hypothesis testing the difference between the two. So I'm going to go second 3, and that's going to give me my L3 with a frequency of 1. And then again, if I look at my alternative assessment, or my alternative hypothesis, I'm sorry, it was that it was less, okay? And I'm going to calculate. So right here, I have all the information that I could need, all right? I'm going to transfer that over to our presentation. So we see from our hypothesis test that our test statistic is going to be negative 2.7759. So if we're talking about our classical strategy, right, our test statistic, our t-score of our null is going to be negative 2.7759. We also see our p-value here, which if we're doing the p-value test, we would need that. It is 0.00901, so just O. Now let's hop over to p-value because that's pretty quick. We're going to compare that to our level of significance. It needs to be less than the probability of getting a type 1 error in order for us to say we have enough evidence, and clearly that is. So this is true, which means that there is enough evidence to reject the null and accept the alternative. Okay, there is enough evidence. Let's go over to classical and kind of revisit that for a second. So here's our T curve, okay, students' T curve. It is symmetrical, if you remember. We are dealing with our difference being less than 0. So if it's less than 0, it's going to be going to the left. It would be left-tailed, okay? We're looking at our t-score of our alpha right now, okay? And our alpha is 0.05. Now, when we calculate t-score, we also need degrees of freedom. So there are 12 pieces of information, so our degrees of freedom is 11. So to find this t-score right now, which is also called our critical value, what you'll need to do is go back into your book. You're going to go to table 7. You're going to look at where it says degrees of freedom being 11 on the left-hand side and follow it all the way across to 0.05, okay? Now, because this t-value is to the left, I actually have to take the negative value of that. So it's going to be negative 1.796. And actually go look at the table. Again, it's table 7. Go look at it and make sure you know how to find it on there. Okay? So now we're going to look at where our test statistic is in relation to the shaded region. If this number is negative 1.76 or 796, negative 2 is definitely in the shaded region. Is it in the shaded region would be the question you ask yourself. The answer is yes. So yes, there's enough evidence to accept the null and reject the alternative. If you were to write this out officially, and I'm not going to write it just because I feel like this pen actually makes some ticking noises in there, you would say something like, there's enough evidence at a 0.05 level of significance to say that the dominant hand reaction time is less than the non-dominant hand. Right? That's what we were testing. Is it less than the non-dominant hand? Okay? Now, this calculation is what we call robust because we do a couple calculations within it, like we find the difference and then we hypothesis test it. So what it means if a statistical calculation is robust, it means that even if there's little departures in normality, okay? So maybe if there's a small skew or something like that, it will not affect the results of your test. However, if there are outliers, you need to check that first, okay? You cannot run a hypothesis test if you have outliers. Now, we did not go over how to find if there were outliers. Okay, we kind of skipped over that and hopped right into it. So let's take a second, go back to your graphing calculator since we have stuff plugged in. Let's take a look at those two graphs really quickly. So over here, graphing calculator, we already have all of our data in. To figure out our box and whisker plot, we're going to go into second y equals, which pulls up stat plot. I'm going to go into my first one. Okay. And I'm going to turn it on. I'm going to create a box and whisker plot with outliers. I'm going to use list 3. Okay. Because that's what I hypothesis tested. All right. Now I'm ready to graph it. If I just click graph, it could be anywhere. I need to go zoom and I need to go down to zoom stat. Okay. Does my box and whisker plot have outliers? No. Is it have a little bit of a skew? I would say kind of. I mean, like this whisker is a lot smaller than this whisker. But again, our calculations that we did when we hypothesis tested were robust, which means that tiny skews like this won't make a huge issue. If the lower quartile, the median, and the upper quartile were all over here, then we might need to reconsider being able to run that hypothesis test. We need to get a larger sample, okay? Now let's test to see if it's generally normally distributed by doing a normal plot. So we're going to go second stat plot again. we're going to go into the one that's on. We're going to go over to the last option. Okay, remember that's our normal plot. We're going to use list 3 also. And we're going to graph it up. So we go zoom, we're going to go down to zoom stat again, and we're going to take a look at our graph. Now, generally speaking, this is not like the size of a parabola. It's not super exponential looking. I would say it's generally linear, so I could agree that this is most likely normally distributed, okay? And again, the fact that it's not perfectly linear is fine because we did a robust calculation, so a little bit of a skew isn't going to be a big deal. So let's talk about confidence intervals now. Okay, let me get our screen back. There we go. So a confidence interval for matched pairs data, because again, matched pairs is synonymous with being dependent, okay, is defined in this way. So we have our D with a bar over it. Anything with a bar means that it's a mean. So this is the mean of our difference. So if we come back and look at our previous one, this right here, X bar, remember what we plugged in for our t-test was our difference. So this number is our difference average, okay? The average of our differences when we subtracted them. Similarly, right here, it's saying we need the standard deviation of our difference. Well, we calculated that here, okay? That's the standard deviation of our sample, and the sample in L3 was the difference, okay? So we have those two numbers. We would plug those in, find our t-score, use our n value, which is our sample size, and crunch some numbers. I am not going to make you do this by hand, okay? Instead, we have a wonderful keystroke on our calculator that's going to hook us up. So we're going to use the data from table 2, and we're going to construct a 95% confidence interval to estimate the mean difference, okay? So our average difference. We do have the actual average distance that we did calculate, right? But that is not taking into consideration that there's variance from sample to sample. So if we're asked to do this confidence interval, it starts off with stat test. Then from there, we're going to go down to 8, which is t-interval. And this is the exact same thing we did before when we were dealing with a t-score, okay? The only difference is that when we get down there to our list, we're not going to plug in L1 or L2. We're doing L3 because, again, L3 represents the difference. And the difference is what we're really looking at here, right? That's even what they say in the question, the difference. So let's take a look at what we got going on there. All right, so I have my graphing calculator up. I'm going to go stat. I'm going to go over to tests. I'm going to go down to t-interval. Okay, because I'm dealing with a mean, interval because I need to find the interval. I'm going to go data because I still have the data plugged in there, and because I had L3 plugged in for my other calculation, it's right here also. Okay, so L3 is already in. I'm going to change my confidence level to 0.95 because that's what the question's asking for, and I'm going to calculate it. And I'm going to rewrite this into my presentation, and there's my interval. Nice and quick and easy, okay? So from my calculator, I got that my interval is going to be between negative 0.0236 and negative 0.0027, okay? So if we were to write our interpretation of this, okay, not just calculate it, but to actually interpret it, we would say something like, I am 95% confident that the mean difference, okay, so the average difference between the dominant and non-dominant hand reaction time is between negative 0.0236 and negative 0.0027 seconds, okay? So I'm saying that interval, I'm saying that I'm confident that that difference is between those two numbers. Another way you could word this is you could say that you're 95% confident that the dominant hand is between 0.0236 and 0.0027 seconds faster, right? Because the negative means that it took less time. So it's actually, this is the interval with which the answer is going to be between, and it's going to be that many seconds faster. It doesn't matter to me which way you word it, but you want to make sure you have some sort of interpretation down. So that's it for the actual lesson. You're welcome to hang around if you want to. I'm going to go over two problems that are similar to your homework. You do not have to do them. I did include them on the note sheet, but they're really just going to review what we just talked about, and I'm going to go through them a little bit quicker. So in number 4, which is very similar to your homework problem number 3, it asks us to do a handful of things. First things first, it's asking us to determine the difference between the set of data. So to find the difference between x and y, so we're going to subtract here from here. Now I'm anticipating having to find the mean and the standard deviation and do a hypothesis test and a confidence interval. So I'm actually going to take a second and I'm going to put this into my graphing calculator. All right, so to put this into my calculator, I go Stat, I'm going to go Edit, and I'm going to clear out all of these first. So over, oops, not Enter, clear, and then Enter, and then over, and then clear, and then Enter. Now I'm going to take a second, I'm going to type in my information for number 4. All right, now I've put all my data into L1 and L2. I double checked it. I'm ready to calculate my difference. So I'm going to go up to L3. I'm going to second and choose L1 and do minus second L2. And again, I'm subtracting in that order because if you take a look over at A, that's what it's telling us to do. Here's our list of differences. I'm not going to write those down on a piece of paper. You guys can see them right now. Next, in part B, it asks to compute the average of the differences, which is what's in this L3 column. Okay, I don't have to add them up and divide. I'm going to actually just be able to do it when I do my hypothesis test. Part B also asks for the standard deviation, which is a calculation I'll get when I do the hypothesis test. So we're going to go into Stat. We'll set up doing our tests. We're going to go to T-test because we're dealing with averages. I have raw data in there. My null is always that it equals 0. My list is going to be L3 still. And I want to make sure that does not equal the null is what I'm choosing because that's what they told me in part C. So take a quick look at that problem. It does say that, and it says that our level of significance is going to be 0.01. So I've got everything plugged in right. I'm going to draw it. And I can see a bunch of information here. I have my test statistic, which is my t-score. I have my p-value for my hypothesis test. This right here, the x-bar, is the mean of my sample. My sample came from L3. That was my differences. So if we're looking at part B, this is the mean of my differences. Okay, it's my x-bar. And the S of x then is going to be the standard deviation of my differences. Okay, 3.8332. So there's our information for B. If we're going to actually do our hypothesis test at a 0.01 level of significance, we're going to look at our p-value. We want to see if our p-value is less than 0.01, and clearly it is not less. That is not true, so there is not enough evidence to accept the alternative. We would instead accept or not reject the null, right? So we're going to keep the null as is, which means that there's no change. In part D, it asks us to do a confidence interval at 99%. Okay, so to do that, we're going to stay right in our calculator. We'll go Stat and go over to Tests. We're going to go down to T because we're dealing with a mean, and interval because we're doing an interval. We have our data plugged in still. We're looking specifically at the difference, which is going to be our third list, frequency of 1, and then make sure your confidence level is 0.99 because that's what the question's asking for. And we'll calculate. And there's our interval along with our mean and standard deviation that we needed for part B. Okay. So let's take a look at one last problem. Again, this one's not that you have to hang on to, but I just want to practice writing null and alternative one more time. So let's take a look at this word problem. Since its removal from banned substance list in 2004 by the anti-doping agency, caffeine has been used by athletes with the expectancy that it enhances their workout and performance. However, a few studies look at the role of caffeine and what it plays in sedentary females. Researchers at the University of Western Australia conducted a test in which they determined the rate of energy expenditure on 10 healthy females, sedentary females, who were non-regular caffeine users. Each female was randomly assigned either a placebo or a caffeine pill. 60 minutes before exercise. The subject rode an exercise bike for 15 minutes at 65% maximum heart rate, and their energy expenditure was measured. The process was repeated on a separate day for the remaining treatment. This means the difference in energy expenditure, caffeine minus placebo, was 18 with a standard deviation of 19. So they're giving us a lot of information here. There are two samples. There is the placebo group and there is the caffeine pill group. Now each person is in both of those. Okay, so one day they might get the placebo, the next day they may get the caffeine pill. Okay, and so that's really important to notice, because that means, because it's the same person doing both, it's a matched pair system. Okay, and then they're calculating what the energy expenditure was by doing caffeine minus placebo. Okay, so they already did all the calculations for us. They got that our average difference is 18 and the standard deviation of our difference is going to be 19. Okay, so they want us to state the null and alternative hypothesis to determine if the caffeine increases energy expenditure. Okay, so if the caffeine is going to increase the amount of energy that someone put forth. So our null is that it doesn't, right? It doesn't change anything. So our null is going to be that our average difference is going to equal 0. There's no difference at all. Our alternative is going to be that our mean difference in relation to 0, okay, so you want to think about that for a second. What's going to happen? What do we want our mean difference to be? Okay, if caffeine, we want that to have more energy, and placebo to show less energy, this would be a higher number, this would be a lower number. A high number minus a low number is going to give us a positive, right? If it gives us a positive number, our mu, or our mean of our difference, should be greater than 0. Okay, again, a little tricky. You got to practice it a couple times to get used to it. So that's our part A. Part B says, assuming the differences are normally distributed, determine if caffeine appears to increase energy expenditure at the 0.05 level of significance. So we will go to our calculator. Okay, to do this hypothesis testing, now that we're over at our calculator, we're going to go stats, we're going to go tests, we're going to go down to t-test. Now this time we are not using data, we're actually using stats. So they're asking us, okay, what is the null statement? It's that it equals 0. What is our average? Our average here was 18. What was our standard deviation? 19, they told us that. What was our sample size? Well, they told us that there were 10 women, okay? And we're looking to see, again, this is why we rate our null and our alternative, if that number is going to be greater. And we'll calculate. Our p-value here is 0.007, and we were testing at a 0.05 level of significance. So that is less than 0.05, okay? Our p-value is less than our level of significance. So because it is, we say that there is enough evidence to reject the null. So we would say, yeah, that we can say there is it's statistically significant increase in energy expenditure when you take caffeine. Hopefully, going over these 2 extra ones maybe provide a little extra support if you needed it, clarified things. Your homework is only 2 problems, so give them a go, and if you have any questions, please make sure to attend my office hours this Friday. Thank you, folks.